When you walk into a dark room, you reach out, you flip a switch, and the lights they just come on.
Right, instantly.
Instantly, yeah.
Mhm.
It's so totally reliable that we almost never, we never stop to think about the intense physical reality of what is actually happening behind the drywall to make that possible. So, welcome to today's deep dive. Our mission today is to literally pull back that drywall.
Yeah, get right into the walls.
Exactly. We are going to explore the hidden infrastructure, the physics, and really the silent battles being waged inside the walls of your home right now. And to guide us today, we are looking at this fascinating set of engineering guides and articles. They were published, I think, between March and May of 2026 by a specialist named John Constantine.
Yes, that's right.
And these come from the team at Burleson AT Electric. They're a local contractor operating out of the Dallas-Fort Worth area, specifically managing the heavy electrical loads in Johnson and Tarrant counties.
And, looking through these documents, what strikes you immediately is that they are not just like basic home maintenance tips.
Yeah.
I mean, they represent a really deep look into the friction between our rapidly advancing modern lifestyles and, well, the physical limitations of copper, plastic, and steel. It's this exploration of how we safely deliver high-voltage energy into the exact same spaces where we sleep, eat, and raise our families.
Which is pretty wild when you think about it.
Yeah.
And that is exactly why this applies directly to you, the listener. It really does not matter if you live in Burleson, Texas, or like halfway across the globe, whether you are living in an older, historic home, managing a modern rental property, or just trying to survive a brutal summer heat wave with your air conditioning intact. The unseen wires all around you are literally the central nervous system of your daily life. Yeah. So, okay, let's unpack this.
Let's do it.
We are going to start with a very real, surprisingly common warning sign that this nervous system is failing. The guides get right into the anatomy of a residential electrical circuit. And the first indicator of a catastrophic failure isn't sparks or like a loud popping sound.
No, it's a smell.
It's a smell. And not just any smell. It is specifically the scent of burning plastic, sulfur, or, incredibly, this bizarre fishy odor right near an outlet.
Yeah, that fishy scent is one of the most misunderstood phenomena in residential infrastructure.
Yeah.
I mean, when you smell that, you are not smelling yesterday's seafood dinner lingering in the kitchen.
Right.
You are actually smelling a chemical reaction. You are smelling the thermal breakdown of urea formaldehyde or the heat-resistant plastics that literally make up the outlet and the insulation wrapping your wires.
Oh, wow. But, we are so hardwired as humans to just think, oh, someone microwaved salmon. We just ignore it. I mean, it's like a home's check engine light, but we don't naturally assume the inside of our wall is basically on fire.
And that is exactly the danger. We normalize this very specific chemical warning sign. The components are actively overheating in there, or they're arsing.
Arsing, meaning the electricity is jumping.
Yeah, arsing means the electrical current is literally jumping across a tiny air gap because a connection behind the wall has become loose, and that creates immense localized heat entirely out of sight. And it risks what engineers call a localized thermal event.
A localized thermal event.
Right, which is really just a very sterile way of saying a fast-moving, incredibly destructive fire inside your drywall.
Man. Okay, but let me pause you there because I'm putting myself in the shoes of someone living in a house built, say, maybe 5 years ago.
Mm-hmm.
I've got a modern electrical panel. If my home is relatively new, shouldn't my breakers just trip if I plug in too much? Like, why would the wiring actually melt instead?
Well, what's fascinating here is the difference between continuous draw and intermittent draw, and really how our modern technology exploits the blind spots of standard residential breakers. Yes, a breaker is absolutely designed to trip if a massive surge happens.
Right.
Or if you instantly exceed the total amperage rating, like, say, turning on 3 vacuum cleaners at once on the exact same circuit. But think about how we use power today.
Oh, I mean, we plug in everything. Everything is charging.
We do, but it's the type of power. Historically, a refrigerator compressor, it cycles on for a bit, then it turns off. It's intermittent.
Yeah.
But today, we have home office servers running 24/7. We have multiple high-end entertainment systems. And most importantly, we have electric vehicle chargers.
Oh, right. The EVs.
Yeah, an EV charger doesn't just cycle on and off. It asks for maximum electrical capacity continuously for 6 to 8 hours straight.
Ah, okay. I think I see where this is going. Let me try an analogy here. It's kind of like water pressure in a pipe, right? A traditional 1980s electrical demand is like turning on a garden hose every once in a while.
Sure.
But modern electrical demand is like trying to force the water pressure of a city fire hydrant through that exact same garden hose continuously all day long.
That is a perfect way to visualize it. The water, or in this case, the electrical current, is moving constantly. So over time, that constant flow creates microscopic expansions and contractions in the copper wiring, just due to the heat. So connections at the outlet get just a tiny bit loose. And when they get loose, the electrical path narrows. That creates resistance. And in physics, electrical resistance translates directly into heat.
So the total amount of power flowing through the circuit might technically stay just like a fraction of an amp below the threshold that would cause the breaker to trip.
Exactly. The breaker thinks everything is totally fine.
Wow. But down at the outlet, that tiny bottleneck is creating so much friction and heat that the plastic is physically baking itself to death.
Precisely. The breaker doesn't trip because the total load isn't technically exceeded. But the localized heat at that loose connection point, it reaches hundreds of degrees. And that is why smelling that fishy chemical odor requires immediate action. Ignoring strange odors just because your house isn't 50 years old is a failure of critical thinking. The system's automatic defense mechanism, the breaker, it's been bypassed by the slow, continuous buildup of resistance.
That is genuinely terrifying. Which honestly makes it a perfect time to look at the brain of this whole operation.
Yeah.
Because if the individual outlets and circuits are acting like bottlenecks, we have to talk about the distribution center that is supposed to be managing all this power in the first place.
Right, the panel.
Exactly. This brings us to the electrical panel itself and how it battles extreme environments. The Burleson contractors spend a lot of time talking about the legendary Texas summer.
Oh, absolutely. The panel is the grand central station of your property. Every single electron you utilize comes from the grid and passes through the bus bars inside this metal box. But as the engineering guides note, areas like Burleson present a very specific infrastructural challenge. You have a deeply varied architectural landscape out there.
Right.
So there are historic homes built 50 or 60 years ago standing adjacent to massive brand new subdivisions.
Right. And those older homes, they have electrical panels that were engineered for an era where the most power-hungry appliance in the kitchen was maybe like an electric kettle.
Yeah, maybe a toaster.
So what does this all mean for someone living in a 1970s house who's trying to run a 2026 lifestyle? I mean, it's like trying to run a state-of-the-art gaming PC using a power supply from 1995. Does this mean older homes are essentially ticking time bombs when a heat wave hits?
Well, if we connect this to the bigger picture, you have to realize that the hardware managing electricity must evolve safely alongside household technology. It means their infrastructure is operating in a state of perpetual stress. Inside that panel are metal bus bars that physically carry the electrical current.
Okay.
In an older panel, those bars were never engineered to handle the thermal load of a central air conditioning unit running continuously for 3 months straight during a blistering Texas heat wave, while simultaneously, powering an electric vehicle charger in the garage. The metal fatigues, the breakers inside the panel physically weaken.
So it's not just a matter of, oh, I don't have enough plugs. The actual hardware inside the box is degrading from the heat of the electricity, combining with the ambient heat of a Texas summer.
Exactly. It's a matter of property preservation.
But it's not just the internal house demand, right? The sources also mention grid fluctuations. What is happening there?
Well, during a severe summer heat wave, the entire regional power grid is under immense strain. Everyone's air conditioning is running at the same time. This leads to voltage drops, commonly called brownouts, where the grid just cannot supply the full standard voltage to everyone.
Okay, and when the voltage drops?
When the voltage drops, your home's air conditioning compressor still needs the exact same amount of total power to run. So to compensate for the drop in voltage, it pulls more amperage.
Oh, because watts equal volts times amps.
Right.
So if the volts go down, the amps have to go up to do the same amount of work.
Exactly. And higher amperage means significantly more heat inside your electrical panel. An outdated panel simply cannot handle that surging demand. It fails. And when it fails, you don't just lose power. You face the very real threat of surges when the grid stabilizes, which can instantly fry the motherboards of modern appliances. So upgrading the panel isn't just about adding more switches. It is about replacing fatigued, underrated metal components with modern, robust infrastructure. It's about adapting your infrastructure to meet current building codes and safely manage future energy demands without, well, burning your house down.
Okay, so we've established how to protect the power once it's inside the house via the panel. We've bulletproofed the inside. But the panel still has to get its electricity from the outside world. To truly fortify a property, we have to look at how that electricity is delivered. And that umbilical cord to the grid is often just hanging exposed in the air.
Yes, overhead lines.
Right. And the Burleson AT Electric guides offer a specialized service to address this, which is underground utility trenching.
Yeah, for over a century, the standard, cheapest method for delivering electricity from the municipal grid to a private residence has been overhead power lines. I mean, we don't even see them anymore. They just blend right into the sky. But from an engineering standpoint, overhead lines are highly vulnerable points of failure. They are suspended in the air, subject to massive environmental variables.
We're talking high winds, falling tree branches, winter ice, all of it. But, you know, I want to push back on this specifically because the guides talk about moving these lines underground into heavy-duty PVC conduit.
Right.
Now, I hear the words trenching, excavation, and PVC conduit, and honestly, all I see are dollar signs and a completely ruined front lawn.
Sure, it sounds invasive.
Yeah. Is tearing up my yard with heavy equipment really worth it just to hide some ugly wires? I mean, it feels like replacing an exposed rope bridge with a heavily fortified concrete tunnel may be a bit overkill. Is it just to make the house look prettier?
This raises an important question about how we fundamentally calculate risk and value when it comes to infrastructure. Yes, removing the thick black cables from the skyline provides an immediate boost to curb appeal. Real estate agents absolutely love it.
I bet.
But the aesthetic benefit is entirely secondary. By removing the specific threats of ice and falling branches, you're looking at physical security.
Physical security against the weather, basically.
Specifically, mechanical stress. Let's look at winter ice storms, which the Dallas-Fort Worth area certainly experiences. When freezing rain coats an overhead power line, it adds an immense amount of static weight to the cable. The line sags. The tensile stress on the connection point where the wire actually meets your house, it's called the weatherhead, becomes extreme.
Okay.
Add high wind shear to a heavy ice-coated cable, and the mechanical force can physically rip the service mass right off the side of your house.
Oh my gosh. Which leaves you with no power and freezing temperatures and with catastrophic structural damage to your roofline.
Right. And no breaker or modern panel in the world can protect you if the physical connection to the grid is severed. But by trenching and placing those lines in durable, high-impact PVC conduit below the frost line, you are entirely eliminating those mechanical variables.
Right, because ice cannot weigh down an underground line.
Exactly. Wind shear cannot snap it. Falling oak branches cannot sever it. Burrowing wildlife and landscaping accidents are shielded against.
You are creating a literal infrastructural shield. So the lawn will grow back, but the physical barrier of the earth and the PVC pipe means your home's connection to the power grid is virtually invincible to surface-level weather events.
Precisely. It is a proactive defense, not just a cosmetic upgrade. The data consistently demonstrates that properties with subterranean utility connections suffer far fewer service interruptions during severe storms.
Okay, I love this progression. Let's look at where we are. We have a fortified subterranean power supply encased in PVC, delivering electricity safely through the earth.
Yep.
It feeds into a state-of-the-art upgraded panel that can handle massive amperage without breaking a sweat during a heat wave. And it distributes that power through clean, tight circuits that don't smell like a fish market. The foundation is rock solid.
It is.
So once you have that robust power, how do we actually utilize it to dramatically transform the spaces we actually live in? And this brings us to a really fascinating intersection of heavy electrical engineering and high-end interior design.
Yes.
We're talking about professional chandelier and luxury lighting installations. Here's where it gets really interesting for me, because I think most of us look at a chandelier and just think, well, it's a very fancy, very heavy light bulb.
Right, just a pretty fixture.
Yeah. But the sources point out that chandeliers aren't just for illumination. They increase property value for landlords, they elevate retail brands, and add luxury to modern homes, often paired with other upgrades, like EV chargers. There are all types: standard, high ceiling for foyers and staircases, modern energy-efficient LEDs, upscale crystal for dining rooms, and commercial.
That's right.
But they also put out massive warnings about the dangers of DIY installations. And this is my question. If we all know how to connect a black wire to a black wire and screw in a light bulb, how much hardcore engineering actually goes into installing a luxury light fixture? I mean, I'm picturing hanging a heavy crystal chandelier yourself is like trying to mount a giant flat-screen TV to a ceiling using just thumbtacks.
That is a very accurate, very scary visual. And the reason it's so dangerous is because you are transitioning from dealing purely with electrical current to dealing with heavy static load and shear stress.
Oh, okay.
Let's look at standard residential construction. The electrical box in the center of your bedroom ceiling is typically made of plastic, and it is nailed directly to the side of a single wooden ceiling joist. It is engineered to hold a flush mount dome light that weighs maybe 2 or 3 pounds.
Right, it just has to hold up a piece of frosted glass, nothing heavy.
Exactly. Now, consider a modern crystal chandelier for a two-story foyer or an upscale dining room. These fixtures can easily weigh anywhere from 50 to over 150 pounds.
Oh, wow.
If you attach a 100-pound dynamic load to a plastic box rated for 3 pounds, the plastic will instantly shatter. Or worse, the nails holding the box to the joist will just pull out under the sheer force.
Resulting in uneven hanging or just total catastrophic ceiling collapse?
Right, and massive code violations. The cost and complexity depend entirely on ceiling height, fixture weight, accessibility, and the necessary wiring upgrades. So, a local Burleson electrician follows very precise steps. By the way, the source mentions Burleson AT Electric handles these targeted solutions at zip code 76028, and they're reachable at 682-343-8629.
Good to know. So what are those actual steps they take up in the attic spaces to make this safe?
Well, before the fixture even comes out of the box, the electrician has to inspect the existing wiring and perform a structural audit. They get up into the ceiling joists. They must entirely remove that standard plastic box. To support a massive chandelier, they install proper mounting hardware, heavy-duty steel cross-bracing that bridges the gap between multiple wooden ceiling joists.
Okay, so they're distributing the weight.
Exactly. This distributes the heavy static load of the chandelier evenly across the structural skeleton of the house, rather than putting all the stress on one single point.
So they are actively modifying the skeletal structure of the ceiling before they even touch a wire.
They have to. Then they install a specialized metal load-bearing electrical box directly onto that steel brace. Only then can they address the electrical side, ensuring the wiring is rated for the specific amperage of a fixture that might have 20 or 30 individual high-wattage bulbs. They are ensuring complete compliance with local electrical codes.
Wow. The ultimate takeaway here is that you simply cannot have the delicate, beautiful elegance of a floating crystal fixture without the hardcore, invisible foundation of steel bracing and strict structural physics hiding right behind the drywall.
True elegance requires an invisible foundation of strict safety. The aesthetic is just the final layer of a deeply engineered system.
Which perfectly brings together the entire journey we've taken today. We started by identifying the terrifying chemical reality of that bizarre, fishy smell, learning that it's the sound of our modern, heavy electrical demands slowly baking the outdated plastics behind our walls.
Right.
And we explored the central nervous system of the electrical panel, understanding how continuous draw from EV chargers and the relentless Texas heat can fatigue internal bus bars, requiring proactive upgrade.
Yeah, you have to upgrade.
Then we push back against the dirt and expensive trenching, only to realize that burying lines in PVC conduit is the ultimate mechanical shield against ice storms and wind shear. And finally, we saw how that incredibly robust power is utilized to create breathtaking spaces, relying on the physics required to hang a crystal chandelier safely.
It really is a continuous narrative. From the PVC pipe buried deep in the dirt beneath your lawn all the way to the peak of your foyer ceiling, it is one single vital ecosystem.
It really is. Your home is not just a static box of wood and paint. It is a living machine. It relies entirely on this hidden network that requires respect, maintenance, and expert care to keep you and your family safe, comfortable, and well lit.
Absolutely. And, if there is one lingering thought to take away from all of this, next time you walk into a room and flip a switch to turn on the lights, take a moment to look at the blank wall next to you. What invisible high-voltage journey did those electrons just take through the dark spaces behind your drywall? And is that hidden path as safe as you assume it is?